Hey, hello there, and welcome back to hopefully the last part of day 12 puzzle of Advent of Code. And I say hopefully the last part because, well, if I don't get to an answer for part 2, I think I'm going to leave this here and just skip it and go to the next puzzle, day 13, because yeah, at this point I'm already like hating this puzzle a little bit, but I want to, if possible, complete it. So okay, this thing has been running for a long time. I think probably more than an hour, and hasn't passed the line. Well, it is processing the line 33 from the input, and the input has 1,000 lines. So I don't think, yeah, I have already checked here what line 33 looks like, and it looks like a bunch of question marks and just some ones as the groups that we have to match. So this is doing a stupid amount of recursion, and it has been munching, like doing millions and millions and millions of regular expression tests for this last hour, and it hasn't yielded any results. Now that I think about it, I could have left this running in parallel, so that lines that are like simpler could have been already completed, and and use all of the cores of my my computer to do this. But well, poor computer, it has been calculating things and yielding nothing. I don't think that this will end anytime soon. The number of possible arrangements for this is probably pretty huge too. But yeah, this brute force solution using regular expressions is definitely not gonna work on its own. So we have done this trying regexes. What the last thing that we can try is doing some caching. I mean, the last thing that I can think of would be doing some caching. And if that doesn't work, I think we would have to change the approach completely and do a more like mathematical approach of really understanding how the combinations or the arrangements of things actually work. But maybe with caching we can cheese your way into an answer. I don't know, but let's kill this thing. Sorry, computer, for having you running something for so well. The computer doesn't feel anything, so there's no problem. But and to think that even to this day there are probably so many computers like crunching hashes for Bitcoin or Ethereum or whatever, and it's just completely wasted time for CPUs and GPUs. That could be used for something useful like playing games or something, but no, apparently inventing like fake money is, well, it makes money, so people do it. That's great. Humans are great. Okay, let's try to restore our faith in humanity by solving a puzzle done by a human for other humans to enjoy. Yay! So how would we do the caching thingy? So the idea that I had was along the lines of we were looking at this thing, the interesting example from the sample inputs, and imagine like the recursion, like we somehow have done the first pattern. We already know this. Okay, and well, there is quite a few things that we can know already with this pattern, I think. Like having calculated the first successful pattern. And Actually, that might be something that we could print on the actual input. Is like that particular line 33 that have been running for so long. Like, did we reach successful patterns? Have we already counted some? I would guess that yes. Like, my intuition says that probably yes, probably many millions, but I'm not sure. But okay, it's like, if we have reached this, like the questions about caching is when to cache and when to read the cache. And basically the idea of having a cache would be in the code. Here we are testing if we match this. Like, maybe even before this, you know, as one of the first conditions would be if cache gets, and I don't know, there's some answer, some count in a cache, and here we need a key, so I don't know, cache key, whatever. That's also part of the problem. If there is something in the cache, then we only return that count, and yeah, that count can be a number greater than 1, because right now we can only say 0 when it matches nothing, or 1, but we never increase the count by like multiples of 1. So this would have the potential of cutting our recursion tree, pruning our recursion tree greatly. But we have to, like, reading the cache, I guess I'm going to try to do it as soon as possible in the recursive algorithm, but it's not obvious to me how to do this, so we have to think a little bit about this. What I was thinking for the cache key is to have some like index, because we already have an index here on this algorithm, which is the index of the first question mark in what we are processing. And okay, like this index represents, you know, to the left of this thing. Sorry, I said to the left, and I noticed that in my face here it will be to the right, but because I'm not mirrored. To the left of this index, all of the pattern there will consist of, well, of dots and hashes, that there won't be any question marks, and so all of that is fixed, and that is something that we already know. And for example, if we were putting a dot, if we're trying out, that dog was, you can probably hear the dog barking. It's from a neighbor that's, well, it's a very excited dog. He always has so much energy. Okay, got dog distracted there. So yeah, everything to the left of that index would be fixed stuff, and that fixed stuff can contain whole groups of hashes. And kind of the idea would be, imagine that we have the first line done, like the first arrangement. This first arrangement should already give us quite a bit of information, I think. Yeah, but let's think about like the second one. So the first one is, okay, we try to put a hash here in this index. Like, imagine we are processing this question mark. We have already fixed this somehow. Like, we have recursively reached this point. We try the hash here, and there is only one arrangement. Okay, great. We should also have like a way to prune and not do 2 to the 4 combinations or 2 to the 3 combinations here to test everything, because well, there shouldn't be any more hashes, but each time we will test a hash, the regular expression will say, okay, no, that's not possible. So it's kind of a linear thing onwards. It's not so much of a problem. Like linear things are not much of a problem, I think. Well, but every linear thing multiplies up with exponential recursion pattern that we have. So the problem, of course, is that this recursive thing is like doubly recursive, and it is an exponential thing, and we need to prune this tree somehow, like do less recursion, and the cache would be the idea to cut that. But we have tried the hash here, then we try the dots, and I think this is kind of the interesting case. We're going to have 3 different patterns with this prefix. This is a prefix of length, how much? 9, I think. So it's 9 characters, but these 9 characters, we know that they sort of contain entirely these 2 groups, the 3 and the 2, on 9 characters. So that is kind of my idea for the hash key would be like 9, like a tuple of 2 things. The 9 of how many things we have fixed on the row, and these 2 numbers, or even like the index of the count of numbers in the group that we have fixed to the left. So after having done this and counted 3 arrangements with this prefix and for these 2 groups, we should store in the cache an entry that says, okay, for a length of 9, a prefix of 9, storing 2, like 9 and 2 basically as numbers, the answer would be 3. And then when we are in this case, it's also a prefix of 9, and it also contains entirely these 2 groups. So we should hit the same cache key, and instead of computing like recursively this answer, we should get a 3 right away. I realized I forgot to put a timer here on my cell phone. Okay, so that would be the idea of cutting the recursion. And of course, this would be recursive, so it should apply in every case. It should also apply for the 2 arrangements in this case, which is repeated a couple of times. So yeah, that's kind of the idea. Maybe the cache explodes in complexity, but no, it doesn't feel like the cache will explode in size either. That's also interesting, and that's also nice. That also tells us something about this thing, because the length of this is bounded, is linear, and the length of this is also linear. So it's a combination of those 2. So it's quadratic. The size of the cache would at most be quadratic with the input. So that's fine. That is polynomial, very bounded thing. Nice. We don't want exponential things. So that would be kind of the idea, right? All right. Where do I push the cache key? We can pass in an argument here, like how much have we fixed already, and we can pass this thing recursively too. So would that make sense? Could be. So in this case, we are putting a dot. Well, let's sketch it out and see if it works. Actually, we could pass the 2 things: how much of the row have we fixed, and how much of the groups have we fixed. And by the way, then we could also optimize the regular expression, because if we have fixed already part of the row and part of the groups, we can even slice into the row and into the groups for checking this is match. We would need different regular expressions for like different sizes of groups, like trimming the prefixes, but that seems like an optimization that is not so much algorithmic. It's more like, okay, we want to cut down a little bit of things, but I think it won't be like algorithmically very substantial. I think that's kind of intuition talking. Everything is intuition talking right now. So let's intuit what we're going to be passing here. It's going to be two indices. It's going to be like fixed index, let's say fixed row idx usize and fixed groups idx index. Okay, and of course these things, when we start calling this here, we have to pass something. And I would like to pass zeros, but zeros are valid indices. But we can use a trick which I've used quite recently for another of these puzzles, which is to use non-inclusive indices, which are really nice because, like, 0, you know, if you have a range of 0 up to 0, non-inclusive, this is an empty range. It doesn't include the 0. So it's like we are passing like the end index, kind of. So the 0 means nothing, and well, we're also going to need a cache to pass around, of course. So let's also receive the, let's call it simply cache. And it's going to be a mutable reference as a hash map of a couple of numbers, usize and usize, and the answer is going to be a u64. Okay, so that's kind of neat. And here for the cache, we are just going to pass a little hash map new as a mutable ref. Sure. Go ahead. That's the initial hash. Now we need a hash key, and that should be it. This count, we need to do the reference for sure. Now the cache key. The cache key, I think, should be what we received as parameters. So fixed row index and fixed groups index. So the first call won't have anything here. That's fine. And now the thing is, we need to generate those things. So for instance, here we are trying, okay, let's follow this along then. I don't know if this is the place to put this if condition, but let's think that it might be. Okay. All right. Here we are considering, okay, if we put a dot, when we put a dot, it might be the case that we are like closing, to say it somehow. Sorry, I'm thinking a little bit ahead of myself. One thing that I may want to know is how many cache hits we have, like how many times we hit this thing, if any. That's probably going to want to, at least for the sample input or something. Cache hit for, and we're gonna have many things. We're gonna have a row. The row is gonna be string from UTF-8. That's, I mean, yeah, from UTF-8. And row to fag. Yeah, sure. Why don't you like this? What's your problem? Is what? Am I not missing, not closing the parentheses? Yes, sure. Come on. Cache hit for this with key. Let's put also the cache key here. It's gonna be this thing and this thing. And the answer is count. Okay, something like that is fine. Just want to know every now and then when I hit those to know that it is working. But we also need to put things into the cache to hit that condition at some point. So here where we count recursively, these are two different things, and I don't know if we can think about them the same way. We can also I wonder if bringing back the if condition for the regex match before calling this recursively makes sense, because we know if we remove this condition from here and instead we call it an if condition before calling even this thing recursively, that still worked, that yielded the same results. And and the benefit of doing that is, what is the benefit? Well, we're gonna not ask the cache, but maybe we do want to. No, that's what we are going to do recursively. That's going, yeah, okay. When we put a dot, the dot is like, imagine again we are on something like this. We have imagine that we are trying. Okay, we try this hash. We try this hash. When we are in this question mark, we don't know. If we look back, we can see a group of 3 and a group of 2, but we don't know if this group of 2 is terminated because we might try a dot that would terminate it, or we might try the hash which would make it a group of 3 and won't match the thing. So I think it is mostly in the cases of dots that we want to fill in the cache, because that's when we can look back and see like the completed completed, how do you call it, like fixed things so far. So let's maybe to put this condition again inside an if. So if this thing, we're gonna do this, and same thing here. If this thing, if it matches, then this shouldn't be needed, I think. Although maybe at 0, maybe it also makes sense, like zeros are also important things to put in the cache, I think. Right? Because that seems, yeah, when we know that there are no arrangements, that's definitely something that we want to put on the cache. So, okay, let me go back to there. It's difficult to think these kind of things. But we have put that. We counted the possible arrangements recursively. What are we going to pass here, though? The amount of fixed things, like the index of fixed things, is going to be this unknown index, because we want to start from there. Unknown index plus 1, I think, because we did a non-inclusive index, right? Then the fixed group's ID, something that we have to calculate now. So I don't know what it is, and then we are going to pass the cache. So let's say, well, let's steal this fixed groups IDX, and let's say let this thing be what? I don't know if this is the correct approach. You know what? I'm doubting myself again. If it doesn't match, wait, this is the same. Yeah. Let me think about something here. Try with that. Possible arrangements is gonna be okay. Caching things is hard. I think that is a known fact. A known fact. Yeah. And 0 and so what I'm thinking, sorry for the long pauses, but it's difficult to think these things through. Fixed, yeah. What I'm thinking is a little bit like, if this is not a match, we're gonna say it's 0. Sure. So yeah, how many completed groups? Yeah, we really want this to be, like, I think I really want this to be like completed groups and not things like halfway through, if it makes sense. So yeah, only when putting, let's only consider, yeah, when putting a dot to cache this thing. What I'm thinking is, does it make sense to pass the fixed group's ID or if we can calculate that on the recursive call, look back, see how many whole groups we have. Because we already know that this thing matches. And so we could just count the amount, the length of groups, I think. Darn it, how difficult it is to actually think these things. If we pass this, got something stupid here. This is what I want. I want something here. I don't know what. Let's think. But after this, we have fixed until this point. If there are also possible arrangements for this, that's another thing. But let's not cache them because we don't know if this group is finished yet. It's going to recursively cache the things when it hits the next dot. So that shouldn't be a problem, I think. This gets called a lot, so I shouldn't be thinking too much. So let's here not have, well, let's declare a variable for this instead of adding to the count. Say let dot case count, and let's this thing, just for symmetry, let hash case count, and then we return dot case count plus hash case count, kinda like this, I don't know. But we have been called, like what we will here in this call, we've looked for this key. So we should also, like we are going to return the answer for these. So I'm wondering if in here and in here I should be populating the cache. Maybe I should. Because otherwise I will be populating the cache. Like I was thinking of populating the cache for this unknown index. Like we put a dot. Yeah, the dot we put in this index. So that is, yeah, that is sort of what we are calculating. Yeah. And where we are caching. Man, this is so difficult to like think of the recursive calls in my head. Here we are recursively calling this starting at a greater index than before. Like we could have skipped quite a few, but shouldn't we be populating this thing that we received? That sounds like the easiest caching like the normal caching approach. Why would I be populating cache for this in here? Shouldn't that be the job of the recursive call itself? Because the recursive call itself I don't know, man. I don't know. I don't freaking know. Fixed group IDs. How difficult it is to think. This fixed group IDs is something that I can calculate now, yes. So let's sketch this. What am I going to put here? Well, I'm going to index the row from 0 up to this unknown index, and including this, well, it's a dot, so we don't need to actually include it. We want to iterate this guy. We want to do something similar to what we did here that I commented. Split by dots and then filter out the ones that are empty, and those are going to be the amount of groups that we have fixed already. So I think goes here, and again this is not an index, actually it's kind of like a count, but fine. So it's actually, let's count this, right? Something like that. For split, oh no, I want to split like this, okay. And I think that's kind of what I want. Let's now call the hash case. For the hash case, we're also going to pass unknown index +1, but this fixed group ID, I don't know if it makes sense to count up to how much I have fixed, because we are trying these. You know what? Let's I don't know why that parenthesis wasn't there. What happened with the parenthesis? Oh, I just deleted it. Let's call this thing a different name than what we received as parameter. So fixed group ID. Wow, just new fixed group, blah blah blah. Beautiful. And here we are going to pass the unknown index +1, the fixed group ID, but the one that we received as parameter, and the cache. Okay, something like that. And we are going to put in the cache. Oh, I closed the editor. Sorry for that. I have a key on my keyboard that just closes the. I don't know why is this the key for. Supposedly turning on the microphone, but I think I have it mapped for something completely different. Okay, this is actually the result, and I realized I could have left that mutable variable that I had before. But now here, I think, is where it makes sense to put things on the cache. So cache insert. The key. Now, what is the key? I think it should be the same key that I looked for before. So it should be this thing, what I received as parameters. And the value will be the count. That's what I think, but I'm not really sure at all. Okay. The question is, does this work for the different things that we have? So let's actually put this like this. Again, because my face is taking space, I didn't fix that. Let's just cargo run this thing with the sample. And I think this is going to be like super noisy. Well, we also got a wrong answer. For both part 1 and part 2. So we definitely made a mistake. But let's not print anything on... let's clean the unused imports. Oops. Sort the imports like you like. Let's not call part 2. Let's not print part 2. Let's run this. We have some cache hits. Possible arrangements for the first one says 2, but I think that's wrong, right? Yeah, it should say 1. So we already have a problem there. That's fine. What did we do? So cache hits. We only got 1 cache hit. That is also like suspiciously low, but how was this cache hit? Let's see the recursive code here. Cache hit for well, the first. Let's see. The sample input is this. So when we did 2 hashes, and why do we have 1 group? Why did we have 1 group? Because we had put, is when we tried hash and dot, we said, hey, hash and dot, the so yeah, the arrangements were 1, but now I'm going to try yeah, that's definitely an error. We are short-circuit in this case, but this is yeah, okay. This is a wrong case. We shouldn't be cache hitting here, because this will be not a match, because it has 2 hashes. Okay, so let's move this condition up here. Okay, which is like the same as asking this condition before calling recursively. So I think it's fine to move it up. Let's run this thing again for the sample. Now we have another answer, but it's also wrong. What we expect to have is 21. But okay, it's wrong in a the first one got 1 arrangement. The second got 4 arrangements, which I think is correct. Okay, but we didn't have any. Oh, we did have a cache key. So cache key hit for these where the known things were up to index 2. So this index, okay. And the amount of completed groups was 0. So in that case, I think, okay, and that said 2, which is cool, because this, I think this one, yeah, this is a case. The second sample input is a case where the hash, like once you computed the first case of having a dot and a hash, for instance, here, and you say, okay, there are 2 possibilities for this, two arrangements for this, and then you want to do the other of hash and a dot. Yes, we should not compute that, because we have completed a group, and it should say 2, and that is what's happening here, and it's giving us the correct answer. So that is fine. But I mean, it seems sketchy how we are doing it. But then for number 3, it was 1 arrangement 2. For number 4, it should be 4 arrangements, and it's not. It says 1. That's a problem. That's a problem. Oh no, number 4 is 1 arrangement. Number 5 should be 4 arrangements, because it's a group of 1 in these 4 places. So number 5, 6 arrangements. We are over counting here, and the number 6, we are screwing it very badly, because it should be 10 and it's now 4. So we are over counting in one case and under counting in another case. Yeah, beautiful. Caching is so easy. Said no one ever. But we of course overcomplicated this code, because I'm not thinking this clearly enough. But let's see. So clearly for case 5 and for case 6, we are screwing. It are the 2 that we are screwing are 2 that where cache get involved. For some reason, for case 2, cache also gets involved, but we still get the same answers. But that might be a coincidence. We are in this case where it's like, okay, we are evaluating up to here, and maybe, like, what should we say in this case? This is the first question mark, and the cache, what the cache says is, okay, when this cache was put by, I don't know whom. Maybe I could print the results of the caches to see if they make sense. But let's see on the 5th case. So cache hit for the 5th case is this. For these, and it's 3, so it's doing 3 plus 3, I think. Yes, but it's not the answer. It is 3 because why is it 3 though? That doesn't seem too good. So let's instead of printing these caches hits, let's print the cache after the call, of this thing. So let's extract this into a variable. No, into a variable. is of course a cache. And let's print line. Yeah, if I print the hash or cache as a debug with nice formatting, how does it look? Horrible. Very, very horrible. So let's do a for loop for key value in cache iter. Okay. Iterator. Should I pronounce things correctly? We are going to print, well, let's say print line. Actually, this print this after the this line. So the cache was, and yeah, let's just simply say key, which is a tuple. So let's print it like this. Value. Okay, great. Let's run this. And we have caches. Yes, yes, yes. Okay. The caches for the first case is always 1, which is not very interesting. For the fourth cases, we have many entries on the hash, which might be wasteful. Okay, let's see the entries for the wrong cases. For this, the fifth case, which is this. So what should we see? When we try out, we always try dot before hash. So we should try dot, dot, dots, and then a hash, right? And when we try this hash, what should we say? Like, I don't know if the cache should help us in this, but let's see. For 0, 0, so this is the end, the final entry that gets put. Well, it is the complete result, so that is wrong because it should be 4, but let's see, 2 and 0 completed things. So if the amount of completed groups is 0, it doesn't seem like a good idea to put that in the hash. It doesn't seem so. Okay, you know what? Let's try to follow my previous intuition, and instead of populating the hash here, we have counted the things when we put the dots, and I think this is sort of, this at least here I think is a correct hash key. So what if we populate the cache here, say cache insert when the key is my cat is playing with destroying my what's left of my computer chair. Here should be this index and this new blah 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 index. The count should be this. Okay. Like, okay, we should know that. Then this is like, do your thing, but I won't cache your thing. And I won't cache this. What happens in this case? We get even smaller answer, even wronger. The first case says 0. All right. After one dot, we see 0 to the left. Okay. Okay. This is kind of wrong. So after one dot and having seen 0, like the arrangements, but the arrangements shouldn't be 0 in that case, right? For the first, no, yeah, for the first case it is correct. That is 0. If we see a dot, like in the first sample case, let's move the sample over here. If we put a dot here, then that is impossible, and so we probably shouldn't cache that. I don't know. Maybe we shouldn't cache that. But yeah, the amount of arrangements is 0. But when we are putting the hash, we shouldn't be short-circuiting there with a cache, because even though to the left we see when we are trying out the hashes, I think that we don't want to check the hash, the cache, sorry, cache, that's confusing. At least the approach that we are doing doesn't make that much sense to see the hash in that case. Yeah, right? Like you can kind of see that. Okay, let's try that out. So instead of checking the cache, here, we're gonna put a dot, and we can ask here if this dot matches something. So if it is a match, or new fixed group 8 things. Thinking. This is sort of the case when we put the dot, is sort of the case that we want to use the cache for. So let's put all the cache code inside there, I think. Right, let's do that. We put the dots. New fixed group IV. Yeah. We see how many fixed groups we have. Up to that index, sure. And now I would like to check the cache. If there is an entry for that, that will be the dot case count. Otherwise, we're gonna call this thing recursively, count the things, and insert the thing on the cache. That's, I think, what I would like to do. And we can keep, like, what if we put a dot that makes it impossible? Well, it's going to say 0, but we still have this, so I think maybe that's good. So let's extract this into cache key. We're gonna have a cache key with this. And yeah, let's say if we're gonna ask the cache dot case count. That's what we want to, this is what we want to compute. If what do we want to do here? Check the cache. If it is something, put it there, and otherwise, I guess we can say if some count, if let some count be in the cache, cache get cache key, then it's the count, man. That's it. Otherwise, we're gonna do this. Count be this. We're gonna return this from this thing, but we're gonna do this. Here it should be a count, and here we should have this. And you're complaining here because if unless having complete types. What? Sure, because this can be dereferenced. Okay. Dot case count cache key. Yes, we try to get. Great. We don't insert the cache in this case. Great. Let's inline this variable then. Just remove this from here. So now we should be finding the cache hits in this case. Okay. Only when putting dots. And are we using? Yeah, this we are not using for anything now. So we can remove this parameter, which was driving me kind of crazy. We don't need to pass this. We don't need to pass this, I think. Never sure about anything. Only 1 0 needs to be passed here. And this, instead of calling this, is like we can say fixed groups count. Fixed groups count. Okay, so let's see if the cache does some, if we still get the same answer. We still get a 12. That seems wrong. Fixed row index, we are also not using it for anything. Okay, that seems bad, but not really. So we have this cache key, so up to here. So we still get 12. That's surprising. Like, we seem to be putting more things into the cache. Second is 4 arrangements. That is still correct, I guess. Third, 4, 1 arrangement. The fifth is 5 is 4 arrangements. So we fixed the fifth case for some reason. So the cache when on position 1, like we are putting a dot on the first index. This is 1 based, I guess. So the known thing, it gives us 3. Yeah, but for some reason then we are really screwing up the 6th case where we're just saying, hey, 1. So that is wrong. That is completely wrong. Let's remove then some of this printing and let's print again the cache hits, which is interesting, I think. We want something like this. Here is the cache hit. Whoops. Uncomment. Cache hit 4. And we are going to have, well, cache hit for the cache key. Yes, and yes, and count, yes. And this is going to be the dot case count. Okay. So how many cache hits do we have? We have some for the second one. So in here, we have already fixed everything, it seems. The position 11? How are we putting this in 11? Oh, it's this thing. Okay. So we're putting a dot there. But okay. Yeah, okay, with a dot it's 0. Sure. Then it also has a cache hit for the 6th, I think it's this, and 1 completed group, and it says, okay, it's, no, I guess 6 will be this, right? 1, 2, 3, 4, 5, 6. Yeah. And we have 1 completed group. So yeah, in this case, it does make sense to say 1. Darn it, I feel like kind of close, but also like kind of far that I'm not really understanding. This cache that I just did. Let's see the last case. So position 10, we have 2 arrangements. No, position 10 and 2 fixed things. So I guess the 10 will be this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes. If we put a dot here, there should, it says that it's 0 arrangements, but that's not correct. There should be 2 possible arrangements here. Should be 2. So we are undercounting, definitely undercounting there. And then here, it should be, I don't know, 3 or, yeah, 3, I think. And here it should be 4, but it's always 0. So that's not good. When we are trying the dots, interesting, but why is that? Why is this 0? So I guess I want to count this parameter of fixed row index is not used for anything, so that's okay. But how did I break this thing with the cache? Because I'm trying to get this from the cache. So if I don't insert in the cache, I should have a correct answer again, I think. Yes, it's 21. Okay, so that's fine. When we are putting things in the cache, they are wrong. Okay, so let's print here, I guess. Print line. Computed arrangements for the cache key, and the count will be count. All right. Yeah, and we are going to insert that in the cache. Many things. Computed arrangements for 9.1. So should we also print the row, I guess? Key. And let's do the same thing. Unnecessary string allocations, but that's fine. For 9.1 0. Why? So 9. Well, yeah, because you only completed one group, and I guess 9 is this. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So yeah, this is 0. This is fine. When we, yeah, okay. 10.2 is our first cache hit. Here's where we put 10.2. Oh, but this is not, yeah, this is not correct. Yeah, okay, we have to, yeah. I think that is the problem. Yeah, so what's happening here is that we are putting a cache key that is invalid. This is this doesn't match the groups here because we are trying out one hash here, and the groups should be 2 hashes. So this, when we put this, yeah, we cannot just cache willy-nilly like this. We need to ask if we pass. So let's grab this thing, our good old regex thing, and say if this thing matches, then let's put everything. If this matches, sorry, let's put from here up to here inside of this if. Beautiful. And only if it matches. We're going to do all of this weird thing. Let's cache key. All right. We insert now. Let's see. Do we get? Oh no, this won't be. We need this. So I guess we can do something like. What we want to do. Sure, let's yank this out of here, put it here. This is horrible, but else it's 0. Does that make you happy? Why not? This is what you should return. Great. Do we have, yes, we are back to 21 and we have cash hits now. Yes, finally. Okay. Now they should make more sense. So after this, I'm wondering if it makes sense to put so many things in the cache, but I don't want to think about that. Let's clean some of the noise, okay, of the printing noise. This is not being used. Sure, let's get rid of it because it just makes me not understand things. Like it makes me confused. Sure. We should still get 21. Possible arrangements for blah blah blah. Okay. Now the moment of truth will be enabled in part 2 again. And where are we printing the possible arrangements for blah blah blah? In here. Let's not print this. Okay, just not print it. We are gonna have the unfolded records that we were already calculating but not printing. And then let's print part 2. Yes, we got back to the same answer as before. Awesome. But now, if we do this and run with the... I don't want to run with the actual input yet. If we run with the sample, but time it, 5 milliseconds. But this is running part 2 and it was taking like, I don't know, but it was like hundreds of milliseconds. Maybe the cache did its thing. Oh, I actually want to print the arrangements now. For the samples, it's like, yeah, all of these, great. I also want to say something like cache size. I'm a bit nervous now. Will this work for the actual input? Cache length, like how many things are we caching? Not that many. Look at this. Even for the gigantic thing, it's like 72 things on the cache. Okay, let's go for the actual input. I am nervous now. Oh, look at that! Yes, look at that go! Is this the correct answer? Oh my god! So I am shaking like I'm a speedrunner or something. Yes! Yes, fuck yes! Oh man, this was so freaking challenging. Yes! Oh, caching is great! Caching is great. Thanks. Thanks, caching. Thanks, hash maps. Thanks, regex and burnt sushi. And thanks, I don't know, what else? My mom, Rust. Oh, damn. Executed in 1 second. That's great. I mean, it's not great, but it's great. Ah, this thing was so difficult. This cache was so effective too. Oh man, I just want to like clean this up a little bit and commit and not have to look back at this problem ever again. This was such a hard puzzle. We're not even using these groups, it seems. That's fine. That's fine, that's fine. We could even, I think. Okay, now we know the actual answer for part 2. That's great. Let's stop printing the 1000 lines. So here, let's comment this out. When we run this, oh, look at it, not printing things makes things so much faster. Okay, this is the answer that we want. Let's copy this. Let's put this in the answers file. Oh man, I was about to give up also. Such a hard puzzle, this thing. Let's clean up some of this, some of that. Row cache, beautiful. Beautiful. Okay, beautiful, beautiful. Everything is just beautiful. This check of the hash here. Okay, now that we know that we have the correct answer, we can clean things up. We can even clean this, maybe, not sure yet. Okay, yes, there's a bunch of things that I would probably want to touch on. So where do we start? Like, this is now review time of what the mess that we did. I want to simplify this as much as possible, really. So fixed group count, this is an interesting thing. Want to do this is fine. Maybe what I want to do, well, let's go let's go by parts. Let's first go back to have a mutable count thingy here. That was just going to be our return thing. Gonna return this hash count. Yeah, okay. We don't do this here. We just do a good old if, and here we increment by this thing. So count plus equals this thingy. Okay, great. Can even oh, this is fine. Let's call this thing C. Beautiful. Okay. Not great. Let's say total count here. Total count. Okay, and here we can put again check this, and if this passes, then total count plus equals this, and this should allow us to not do this check, I think. So if we run now in release blah blah blah, okay, it doesn't seem to change the runtime. It's around 700 milliseconds still, but the answer is still the same. So that's good. So that is one idea. Sorry. Another idea, though, is can we make this this caching algorithm actually more apply for both of these cases? Fixed groups count. Not sure. Let's try it. Yeah, let's try it. Although I'm not sure if it is the best thing. We close this up here. Let's see if I try to put this out like here plus the cache key. Okay, it's like we put this is going to need to change. I have to fix this to work for both the dot and the hash, but if we move it out, then we can maybe check the hash. Yeah, let's sketch this out. So we are up to no, actually this doesn't make much sense, right? Because I would like to early return in this case, but how much this is like up to this question mark. But how much we have completed. Well, we can have this filter. We don't want to ignore the left part. I don't know if thinking of making this generic is the right thing to do right now. Let's go back to something that I know works. This we know that it works. Right, gives us the correct answer, even though it takes 700 something milliseconds. Maybe not recording it will take a bit less. This is something. This is a trivially parallelizable problem. So that's something that we can do. We can stop passing these groups around. What I was thinking is, if we do this count of how many groups we have already fixed, but instead of just counting them up, I would filter the slices of, because here we're splitting by dots, filter the different slices, the rows of hashes, and zip this thing with, here I would do something like zip this with groups. Yeah, just groups iterator, and then filter the ones that are equal to the size of the group. The thing is that if there is something that is not equal, then that means it's not a match, or that we haven't completed that group and it's the last one. So I think that's like an overcomplication. It's probably possible to do so, but let's just clean this code of warnings and things like that and commit what we have. Okay, so there's a lot of things that we could improve in here. Positive arrangement sum, regex, this is horrible. We can inline this thing. Why doesn't it let me inline? That's interesting. We can pass this in here, right? Yes. We can pass also the cache in here. Don't care about this. Don't need to zip this. The regex generation is actually quite nice. Parsing records is fine. Unfolding this input is horrible. I don't like that, but it works. This is questionable, but yeah, let's clean the code. Total count, yeah, okay. Let's clean this up. The groups are not being used, so let's ignore them for now. I mean, I think I don't really like this, but I mean, this should be removed, to be honest. We have the records, which have this, okay. Yeah, it's like if I'm not using the groups, let's just simply not use them and not pass them around. We can reintroduce them if I optimize this further later, I can reintroduce this because we have the groups here. They are at hand. We can totally do this. Okay, that is quite a cleanup already. There are no warnings. Still runs. That's great. We can even run the check all command, which I think should pass. Yes, it does. Okay, so this is already, I think, an acceptable solution. The only horrible thing that, okay, here we are counting this for answer for part 1. For part 2, we are unfolding completely the unfolding the input again, and this is something that I don't particularly like. And I'm wondering if it will be easy to change this, but let's add all of these changes. The readme, we can get rid of the plan, but it was a very nice plan because it worked. We can add this. Instead of unfolding the inputs, I would like to unfold the records themselves. So how are we going to do that? Can possible arrangements some, because we are unfolding the input and then parsing the input again is kind of stupid thing to do. But let's see. Parse a record. A record is okay. We have this. Oh, because we are also using an array of slice of bytes that comes from these strings. Okay, is that a problem? I don't think so. I don't think so. Unfold input. Unfold records. This thing is a vector of records. Yeah, so it's an owning thing and then non-owning thing. That's kind of a problem, I think. Let's just make it 2 vectors here. So it's gonna return this and this. Vector of bytes and vector of thingies. Here we can just say 2 vector. And isn't it happy? Let's call this thing row. And group numbers. Okay, that's what we are doing. No need to say nums here. Numbers strings row. Eh, sure. Springs row. I mean, that refactor didn't add much, to be honest. Let's inline these things again. I go back and forth, but yes, the name was already nice in both cases, so that's fine. We have that, and then when we count possible sums, here we can still get these vectors, right? Since this is a tuple of two things, I guess we can do this. And that is fine, although it's the same to say clone, right? Let's say clone. Just, clone the thing. No worries about cloning things in the high level. Parse record, I wonder why it wasn't complaining about this before. Huh. Weird. Kind of weird. But sure, let's do that if you're happy with that. These are going to be the records. And like when we unfold them, parse record generates groups of records. Yes, okay. When we unfold them, we are doing it with all the input. But instead of that, can we do something like unfolded records be just modify the records, right? We could even have these things as a mutable thing. Yeah, why not? Unfold it. And that's it, right? How we would unfold a record? It should be quite easier. Although we can write it. Yeah, let's say unfolded records is going to be the records. Just remove all of this. We're going to consume them. Why not? Map and say unfold record and collect. Okay. And unfold record is going to take. We probably want type alias for the records, which are these things, but let's go with this. Record will be this, a tuple of things, and it will return a new record. Like it's going to consume it. And we need to have the springs. So okay, the record is going to have, it's a tuple, so springs row and group numbers. So it's going to return a new record, which is going to be the springs row. How are we going to do this? Well, we can repeat this, take 5, as we were doing kind of here, and then join. This join is from iter tools, but it only joins into one string separated by, take 5. We don't want to like just join, we are sort of like folding. Oh, and this is an array of bytes. You know what? Let's just do it like let's unfolded row be it's a mutable thing, springs row, and let's mute unfolded group numbers be the group numbers, and then we're going to do for 4 times do unfolded row push one of these, and I realize now that I'm going to want to push folded row append extend what does extend do? Extend operation. Let's actually clone these things because we are going to need strings row and the folded group numbers also extended with the group numbers, and that's it. We are going to return then the unfolded row and unfolded group numbers. Is this correct? Then like this, value of moved this. Where does it get moved? So it gets moved when we call extend, sure. Do you like this? Yeah, you like this. That's what I want. Does this still run? Yes. Is this better than what we had before, actually? I don't know. It's like, yeah, it's fine. But I would like to join iterators, have like a join with function, like springs row. We iterate over this. We only have, oh, look at this, merge join by from iter tools. What the hell? Create an iterator that merges items from both this and the specified iterator. Ooh, fancy, but that's kind of not what I want. Just want to repeat this 5 times and yeah, just put 4 more of those. Well, one thing that we could do, it's like, okay, this works, we know, but we could also express this as these, and then like join, let me think, like join 2 iterators, and the other are like a repetition of this and this. Like iterators can be joined, right? I don't remember if it is like concact. This is from iter tools. join. Well, that's also for it now, but I'm pretty sure that there is like in the Rust standard library like Rust combine one iterator after the other. Merge two iterators into the same vec. Chain is what I want. Chain. So yeah, that's kind of an idea. We're chaining things, so we can express this like this, but we can also say, okay, Springs row, make it an into iterator. No, because we actually want to. So iterate chain, iterate clones, because otherwise it's going to be a reference chain, and then repeat the Springs. Let's move this down and say, okay, this is one approach. Great. The other one is going to be repeat this. Take 4. And even instead of saying repeat this, what I want is like repeat one that is a 1 and these. So there's also an iterator. Here we got a repeat. Yeah, this is iter repeat. I'll actually import just this because I like using the names, the prefixes. Iter repeat, and what are we going to do? Well, iter once the byte of this, and then chain again, chains with Springs. Don't you like this? And Springs cannot find value. No, Springs row. And okay, if we do all of this and we say collect, that's sort of what unfolded row should be. Then we're going to return the unfolded row. And this doesn't like this because yeah, what we are repeating here are iterators themselves. Sure. What do we actually want? This is like an iterator of iterators. We actually want to repeat whatever, but then it's like we want to flatten this thing. Can we do that? Like flatten. Then this collect is okay. I think that actually kind of worked. We will also need this. Let unfolded group numbers, and we're going to return that. And again, this is wrong. It's difficult to. Now this is much more unwieldy than this simple imperative loop. So this is fine. Unfold the record. So we're doing that. That's great. We have the original records, the unfolded records, and that's fine. We can remove this. all of this is fine. Okay, that is pretty good. If we run, we get the answer in 700 milliseconds. I think as far as code shape goes, this is already quite alright. And before I close this video, I would like to do some low-hanging fruit optimizations to reduce this number. So we have already done like the high-hanging fruit optimization of like trimming the recursion by using a cache, which was great. It was so great. Now there is two things that we can try out pretty quickly. One is Rust C hash. Try out a better hashing function, which is just this guy, Rust C hash. Sure. If we do cargo add this. Cargo toml. Yes, rusty C hash. And does this have? Yeah, it has another name, fx hash map. So we're gonna use this, but I like to just call it hash map. Maybe the constructor needs to be called default. So sure. And this should just be like a drop-in replacement for the hashing function. And hopefully it will be, oh, it's nothing. No, it's not faster at all. Okay, I thought it might have been faster, but it wasn't. So we have tried a faster hash and it didn't work. Great. Let's go back to built-in hash map and let's cargo remove this thing. Why is it not in the dependencies? I mean, wasn't this just 2 seconds ago? Cargo toml? Oh, it is because it's called something else, like this? Okay, yeah. That's all right. And the other thing that we could try is, again, cargo add, but this time let's add Rayon, which is awesome. And Rayon provides parallel iterators, which is what we could use here. Instead of saying just iter, we can say par iter. And yes, it is from iterate Rayon blah blah blah. I think it just has a prelude that we can, if we do this, no, not like this, but like this. Are you okay with that? Yeah. Okay, so now we should be computing all of these arrangements in parallel instead of sequentially. So if we run, well, after compiling the Rayon dependencies themselves, which seem to take some time, usually, luckily then, cargo does this faster once you have compiled it once. And look at that, it's the same number as before, but now instead of 700 milliseconds, it's like 170. So it is kind of super fast. And that is something that I will want to do in this case, so that when checking all of the results, this is taking a lot because it's compiling Rayon again for debug build, but after that, this should be fast. And okay, adding Rayon was pretty easy. And man, this puzzle was something else. So difficult for me to think about this like combinatorial things, but the hash really did work wonders for this thing. I wonder if this, I should comment something, but like it's okay. I think I can follow this up. I'm trying this. If this is a match, we see how much we have done. Okay, here if we have a yeah, this is maybe not the greatest thing ever. I would like to say something like, isn't there get or insert? I think that there should be Rust hash map get or insert. Pretty sure there's like the entry thing. Yeah, entry. If it's occupied, blah blah. Or insert with. Yeah. That is what I want, I think. So we should just say, hey cache, give me your entry. So this is going to be just this. Or insert, and this takes a value, or insert with, and this should be a function that will do the computation. And yeah, we don't need to insert, we just do this and clean all this mess. And okay, what do you want here? Expected at tuple. Okay, now it's not a reference but this, and this is probably because cannot assign. What does this return actually? Cannot dereference this? All right. But it's already borrowed. What? What's going on? Borrow occurs here, closure construction occurs here. Yeah, we're doing or insert with, but we are calling this. So yeah, I think this looks much neater, but we actually need to call this thing recursively with a mutable cache. So this won't work. Yeah, this cannot work actually, because yeah, thanks Rust for this. This is something that would be nice to express, but this cannot work because when we call this thing recursively, like this recursive call can insert things on the cache itself, so it needs a mutable reference. And this thing that like gets an entry for this key, or if it's not present, it's like, okay, holds the entry itself and lets you insert into it. Like it cannot hold that while you call this thing recursively, because like the place where that entry goes can shift away when more things are inserted into the cache. So that was a good effort, but it didn't work. We could probably still make this better somehow. So this is, yeah, adding this to the count, to the total count. I think this is fine, right? Oh, we can do it with let count this. Can this be expressed with let else? Like let count be this thing. Maybe count can be mutable. Not entirely sure. Let's say that can be this, or else get this thing from the cache. Something like this. That's it. And then do total count plus equals count. You cannot assign there because it's not in this scope. Even if we put mute here, no, it doesn't make sense. But we can. Say let count be this, but you don't like this because else clause does not diverge. The else is like for early returning things. Okay, now this is why am I trying to do clever stuff? This is not the time for clever stuff. Let's go up to here. The optimization of using Rayon was great. This is some code that I'm not very fond of. Maybe written with a match is better. Not really, but no, it's kind of the same thing. Okay, let's leave it as this. Cannot think of a better expression for that now. And yeah, all the rest is pretty good, I think. Let's sort some of these functions of how they are used. So possible arrangement sum. I want our little recursive function to be immediately after this, because this is like the meat and potatoes of this problem. Then unfold record can be last because that's not very interesting. And this, yeah, this is fine. Okay. And I think that is our final solution. Cargo, yes, added Rayon, that is fine. It's a good dependency to have. Let's say, actually, yeah, well, add the 12 solution. I'm pretty sure that we have, yeah, we have some work in progress and things like that. So let's rebase, yeah, let's say git rebase interactive up to here. Ooh, what did I do? Oh no, main. Yeah, I screwed up. It should be origin main. Why? Okay. So we are going to pick everything, but let's reward this and let's do a fix up of these two others. So okay, add day 12 solution. So we remove the work in progress commits. Okay, that should be good for this solution, and I want to end this video. Before doing so, let's do as usual our, why am I using bash here? Because we used bash for something. Our usual thumbnail. So it's been a while. So this is day 12, and this is actually the third video of this. So how do we call this? Suffering, basically. But no, let's give it a more hopeful title. Yeah, we did caching and regex. So basically it's regex plus caching and let's say equals win or equals success. Yeah, and a smiley face. Let's see how this looks. The smiley face could be, yeah, could be a more smiling smiley face. That looks nice. Let's pass it to a lolcat. Let's clear the screen. Let's do this, and let's put this to the side. And as usual, when I put things to the side, it screws things up a little bit. So let's clean this. Oops, clear the screen again. Run this again. Not sure about the colors. I got the same colors. Okay. Yeah, regex caching. It is success indeed. All right, and we can have, I don't know, some of this code, this horrible code up to here. Look at this beauty. Cache, regex, that's a beauty. All right, I think that will be it for today. It's gonna be another two-hour long video. Sorry for that, but well, that is what it is when you get very stuck on a puzzle. So if you have been, thanks for watching and see you later. Bye bye.